In this video, we're going to talk about Taylor series and what they are. So I want to begin with a definition. The Taylor series of a function f of x that's centered at a is an infinite Taylor polynomial. So we ended the last video by giving a definition of what a Taylor polynomial was. They look like what I have here, like f of a plus the derivative of f at a times x minus a over 1 factorial, and we keep going like this. And I've gone ahead and written this in sigma notation as well. But overall, what this is now is it's an infinite polynomial. And it's infinite because I ended it with a plus dot dot dot. So the f of a is some constant. I'm calling it a naught. The f prime of a times 1 factorial, that's also a constant. I'm calling that a1. F double prime of a over 2 factorial, that's a constant, a2. And so on. So the general goal when we talk about the Taylor series of a function is to figure out what are these coefficients. What is a naught and a1 and a2? So in general, an is going to be the nth derivative of f evaluated at a and divided by n factorial. Okay, so I'm going to erase some of those lines that I drew to not clutter this picture. But let me go ahead and highlight this formula because this is important. This is the formula for the coefficients of my Taylor series. So a Taylor series that's centered at x equals 0 is called a Maclaurin series. Okay, so this is basically saying that a is 0. So if the a in that formula is 0, we call our Taylor series a Maclaurin series. So Maclaurin series is actually just a special type of Taylor series. So let's do an example. Let's find the Taylor series of the function f of x equals ln of x at x equals 1. So this means that a equals 1. All right, so what this question wants is it wants us to approximate ln of x with its Taylor series. And the Taylor series is going to look like, there's some constant term, a naught. There's some a coefficient of a degree 1 term, except it's not just going to be a1x, because I want it to be centered at 1. It's going to be a1 times x minus 1. The next term would be a2 times x minus 1 squared. So when there is a non-zero value of a, when I write these terms, I have these x minus a to a power showing up. So if I go back and look at the general formula, notice here as well, we had these x minus a's to a power. In the last video, we looked at a problem where a was 0, and that's why it just went away and we just had x. All right, so let's go back to our example. All right, so let's recall, oh, and whoops, I forgot to put the plus dot dot dot. So this is going to be an infinite series. All right, so let's recall our formula for our coefficients. So let's recall that a sub n is the nth derivative of f evaluated at a divided by n factorial. In our problem, a is 1. Okay, so let's start to evaluate these coefficients. Okay, so our function f of x equals ln of x. All right, so if I want a sub 0, that's going to be f0, which looks a little bit weird, but I'll explain what that means. Our value of a is 1, and then over 0 factorial. All right, so what f0 x means is just the original function. It just means f of x. That's what that notation means. Okay, so that said, if you take ln of x and you plug 1 into it, and 0 factorial, that's 1. Well, ln of 1 is 0. And 0 divided by 1 is 0. Okay, so we got a sub 0. A sub 0 is 0. To get a sub 1 is going to be the first derivative evaluated at 1, and then over 1 factorial. So for this, I'm going to need to know what the first derivative of my function is. The first derivative of ln is 1 over x. Okay, and I'm going to be plugging 1 into that, which is 1. 1 factorial is 1. And 1 divided by 1 is 1. So let's keep going. Let's go to at least the fourth derivative. So let's do the second derivative. Second derivative would be negative 1 over x squared. So that will let us figure out what a2 is. a2 is going to be the second derivative evaluated at 1 over 2 factorial. So now I'm going to be plugging 1 into negative 1 over x squared. And if I do that, I get negative 1 on the numerator. 2 factorial is 2, so overall I have negative 1/2. Okay, so let's do a couple more. So the third derivative would be 2 over x cubed. So we can use this to figure out a3. a3 is going to be the third derivative of f evaluated at 1 over 3 factorial. Plugging in 1 into 2 over x cubed, we get 2. The denominator is 3 factorial. Let's just leave that as 3 factorial. Actually, no, let's simplify that. 3 factorial is 6, and 2 over 6, that's 1 over 3. Okay, let's do one more. So let's do the fourth derivative. So typically when a problem says to find the Taylor series of something, unless a question specifies how many terms to figure out, and in this question it didn't. If it doesn't tell me how many terms to figure out, I need to figure out enough until I see what pattern there is in the coefficients. So maybe let's do one more. So if I take the derivative of 2 over x cubed, we get negative 6 over x to the 4. And now plugging in 1, we get a4 is the fourth derivative. Let's plug 1 into it over 4 factorial. And then plugging 1 into this, I get negative 6. 4 factorial is 24. So we end up with negative 6 over 24. That is negative 1/4. So at this point, I sort of start to see a pattern emerging in the coefficients. It seems like the terms are alternating. So I see positive 1 and then a negative 1/2, positive number, negative number. And the denominator keeps going up by 1 every single time. So at this point, I think we have an idea of what the Taylor series is. I think, okay, so the very first term coefficient was a 0. So I don't need to write that one. The next coefficient is going to be a 1. 1 is the coefficient of the x minus 1 term, the degree 1 term. And then I have, the next term would be the x minus 1 squared term. And its coefficient is negative 1/2, so I'll write minus this over 2. Okay, and then I'd have plus x plus 1, minus 1. X minus 1 cubed over 3. That's from the coefficient being 1/3. That's for the degree 3 term. And then I'll have minus x minus 1 to the 4th over 4. And then plus dot dot dot. Okay, so if we were to write this in sigma notation just to practice, this would be the sum. So I know that I'm probably going to need like an x minus 1 to the n term in this to give me those x minus 1 to a power. And if I do that, the very first power is a 1. So let's start our sum at n equals 1. And it'll go to infinity. And the denominator sort of always matches up with the power I have on the top. So when the power on the top was a 2, the number on the bottom was a 2. So in the general formula, if the power of x minus 1 is n, I need an n on the bottom. Okay, so the last thing I need something to give me that alternating part. So the alternating part is usually something like negative 1 to the n, or maybe sometimes like negative 1 to the n plus 1. Usually it's something that looks like this. So in this case, let's just try negative 1 to the n first and see if that works. If we were to try negative 1 to the n, the very first thing I have to plug in is n equals 1. And if I plug that in, the negative 1 to the n becomes negative 1. So that's saying that the very first term in this should be negative. And then when I plug 2 into it, I would get negative 1 squared, and that's positive 1. So that would be saying that the second term is positive. And that's not quite right. That's the opposite of what I want. So I'm going to make this an n plus 1, and that's going to fix that. Now when I plug 1 into this, the power is even, and negative 1 to an even power is going to be positive 1. And that matches up with the fact that the very first coefficient is positive. Okay, so that's what it would look like in sigma notation, just for practice. Okay, but my Taylor series looks something like this. So that is the Taylor series for the function ln of x at x equals 1. All right, so the key to this, the key to finding a Taylor series was determining what these coefficients are. So when I find the coefficients, either the problem will tell me like how many terms I should write up until. So if it tells me to write the first 3 terms, I should write the first 3 terms. If a problem doesn't tell me how many terms to write, like this one, I need to write enough terms to where the pattern is clear. Okay, so now I want to give a list of just some very common Maclaurin series. And remember, Maclaurin just means a special type of Taylor series that's at x equals 0. That's centered at x equals 0. Okay, so there are 4 really, really common Maclaurin series. And we've actually sort of derived 2 of these. In this section, we've sort of derived number 2, the one for e to the x. We did up to a degree 5 polynomial, but I think it wasn't hard to see that this pattern was going to continue, where the terms all look like x to the n over n factorial. Okay, the very first formula we've sort of seen in an earlier section. Let me briefly talk about the reason behind why formula 1 is true. So when I look at 1 over 1 minus x, this looks like a over 1 minus r. So that makes me think, oh, geometric series. That makes me think of geometric series. And just matching this fraction up with 1 over 1 minus x, that would imply that a is 1. That would be my first term. And indeed, that's what I see for the first term. And the r value is x. And looking at my series, that is what's happening. To get from one term to the next, I keep multiplying by r, and then r again. Okay, so the fact that this is what a is, the first term, and that's what r is, that matches up with this series I'm seeing. This is a geometric series. And it turns out that this formula for our geometric series is true when the value of r, when its absolute value is less than 1. That's where I got this condition, the condition that absolute value of x needs to be less than 1. That's when our geometric series converges to this formula, and we had seen that before. And then formulas 3 and 4 are the Maclaurin series for sine x and cosine x. So notice a couple of things about these. So for sine x, notice that sine is an odd function. It's an odd function. And that sort of makes sense based off of what we have on the right-hand side, because all the powers we have are odd powers. It turns out when we have a polynomial with all odd powers, it ends up being an odd function. Okay, and for cosine is an even function, and that is matching up with what I see on the right-hand side in terms of its series, its Maclaurin series, which is just a Taylor series that's centered at 0. These are all even powers. When we have a polynomial that has all even powers, it'll be an even function. That's something that's easy to check. And I've gone ahead and written all of these in sigma notation. Notice that both sine and cosine alternate, and that matches up with what I see in their sigma notation form, because they have that -1 to the n. That indicates there's that alternating part happening. Okay, so notice that formula 1 is true for a limited range of x values, just when the absolute value of x is less than 1. But formulas 2, 3, and 4 are true for all values of x. And that means that whatever this Taylor series is, this infinite polynomial, it will be equal to this function exactly for all values of x. At least when I consider an infinite polynomial. So we can show why this is true for all x using Taylor remainders. And that is section 10.9. That's the next section. All right. All right, so let me list one cool result. Technically, it's one cool result, and then sort of a warning. All right, so here is the cool result. So notice, one of the things that I get to do, now that I have these formulas, these infinite polynomial representations, is I can plug in anything that lies in whatever interval this formula is valid for. So something like formula 2, it's valid for all values of x. So what happens if I plug in something like x equals 1 into both sides? Well, if I do that, on the left-hand side, we just get e to the 1, which is e. On the right-hand side, I get 1 plus, I'm plugging in 1 for the x. I get 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus dot, dot, dot. So that is kind of cool, at least in my opinion. The fact that this series here, it's sort of like the reciprocals of all these factorials, weirdly adds up to just e. Okay, so that is one powerful thing that we get to do with these Taylor series. Okay, and now I want to give sort of a cautionary warning. So there's one thing I want to be careful about. So if we try to do the same type of thing from formula 1, so from 1, let's go ahead and plug in x equals 2. So let me just zoom out so we can see 1 a little bit better. Okay, so I can see formula 1 a little bit better. Let's plug in x equals 2 into that. So on the left-hand side, if I plug in x equals 2, I get 1 over 1 minus 2. On the right-hand side, I'll get 1 plus 2 squared plus 2 cubed plus dot, dot, dot. I got my geometric series going on. Okay, and if I simplify, the left-hand side, the fraction is negative 1. But the right-hand side is clearly infinity. It's a huge number because they keep getting bigger and bigger and bigger, and I keep adding these bigger and bigger numbers. But those aren't the same. Negative 1 is not the same thing as infinity. So sad face there. Why did that happen? Why are these not the same? Pause the video for about 1 minute and see if you can figure out why we're running into this issue. 4, 3, 2, 1, pause the video. Pause the video for about a minute and see if you can determine why. All right, so hopefully you've done that. Hopefully you've paused the video for a minute and really thought about this. If not, go ahead and do so now. So let's talk about this. The issue is we plugged in x equals 2. But remember that we're talking about a geometric series. And a geometric series converges when the absolute value of the ratio, when the absolute value of x, is less than 1. But for the number 2, it doesn't satisfy that. The absolute value of 2 is not less than 1. So when we plug 2 into it, the series, the geometric series, this thing on the right-hand side, should have diverged like we got. So this formula here said that 1 over 1 minus x was equal to its geometric series only when the absolute value of x was less than 1. So I could plug in anything where the absolute value of x is less than 1, but I didn't do that here. I plugged in something outside of that interval, and that's not allowed. All right, so just to conclude now, I want to state an important fact. So the Taylor series for a function is going to be equal to the function. So what I mean by that is the Taylor series will sort of converge to the same value that the function has on some interval around a. And the question I want to ask is, how do we know when they're equal, when the Taylor series is actually going to be the same thing as what the function is? And the answer to this is, we use the remainder theorem for Taylor series, and that we'll talk about in the next section, in section 10.9. But in the next video, we're going to talk about how you can use a Taylor series that you already know to quickly get formulas for new Taylor series.